Thank you, Julian. Yes, so I'm here to talk about reference capabilities and how we use these to program object-oriented in an object-oriented fashion in a concurrent setting. So, whenever you go to use a data structure or an object, apart from the obvious question of if the thing is correctly implemented, you have to ask yourself things like, is this thing aliased? And does it encapsulate its representation? And as soon as you go to a concurrent setting, you get tons of other concerns. Not only do you have to worry about aliasing, you have to think about, is this thing going to be accessed concurrently? If it is accessed concurrently, is the object thread safe, or can there be data races? You have to think about, are all the views of the object thread safe? And if the thing is thread safe, is it internally synchronized, or do we need to explicitly synchronize, like take a lock or something? So using a very classic example, here's a program with two variables, C1 and C2, which are pointing to some counters, and we increment them both, and in the end we want to know if C1 has increased its value by 1. So in order to reason about this program, we have to know if C1 and C2 can alias or not. In the concurrent setting, we still have to think about if they may alias, but we must also think about if the objects are properly synchronized. So if there can be concurrent access to these things, and there can be data races, maybe there are problems like lost updates and whatever else data races can bring. And it's not only the increment methods, but also we need to think about the increment and the value methods, if there are any races between those. So there seems to be an obvious solution to this, and that's just put locks around everything, and then we should be safe. But of course we don't want to do that, because if we lock everything, then effectively we're synchronizing, we're sequentializing all accesses, which hurts performance. But on the other hand, if we lock too little, then we might lose correctness. So we want to find that sort of level of just right amount of locking. As another example, consider if we're performing a data parallel operation, for example, a parallel map over a tree. So we want to do some kind of divide and conquer style parallelism. So we have to think about, can two nodes alias, i.e. is the data structure eligible for divide and conquer style parallelism? Can two elements of the tree alias? And if they can, will that lead to data races? Maybe two elements can't alias, but they can reach the same state, and so we can have data races by that. A similar example is one where we have a task parallel program. So, for example, when we want to map two things over a tree in parallel. So we have the same concerns as before, but we also need to think about what happens when we apply two operations in parallel to the same element. We need to know if these operations are commutative. Finally, let's look at a software engineering point of view. So if we have a list that works in a sequential setting and we want to make something that is thread safe, what we might do, one approach, is to take this list and wrap it in some other class that just uses this list but wraps the access in locks. So as you can see, there's a lot of boilerplate. I think Java's linked list has 34 methods, and you need to keep those in sync if there are changes to either side. And of course, keeping this in sync is error prone. We need to make sure that we're not making mistakes here, even though we want these operations to always do the same thing. So in summary, when we're looking at a piece of code, it's usually very hard to know if we need some kind of aliasing, any concurrency control, without looking at the full program. And on the other side, it's hard to know when you're defining a class or a type how this thing is going to be used. So it's hard to build in this concurrency control, because you might not know how the object is supposed to be used. And finally, an observation is that the business logic of a class and the concurrency control are often orthogonal concerns. So with these things in mind, let's go to see how we try to tackle these problems. So in general, a capability is a token that grants access to some resource. And in our case, a reference capability grants access to some object. So for the rest of the talk, I'm going to be talking about capabilities, but actually I mean reference capabilities. So a capability has a type, and this type defines the interface to the object. And so by now you might be thinking, well, this sounds just like a reference, and that's basically what it is. It's merging the idea of capability and the idea of a reference, with the important property that a capability assumes exclusive access to the object. Not necessarily that it is the only alias of the thing, but when we are inside the object, we want to exclude the possibility of there being another thread inside the object at the same time performing updates that we might see. Should also note that data races isn't, while it's the property that we reason about, it's not necessarily the end goal. We can use the property of having no data races to express things like atomicity and so on. So as we saw, unless we resort to a lot of locking, it's hard for the implementation of a class to provide proper concurrency control. So what we do instead is that we give each capability a type qualifier that we call its mode, and this decides why or how thread safety is achieved. So as an example, we can have an exclusive capability, linear capability, and the linear capability is globally unique. This is your run-of-the-mill linear pointer, unique pointer, and access through this is trivially thread safe, because if we could access it, we were holding the only reference to the thing, and so there can be no other threads doing updates at the same time. We could relax this a little bit and allow aliases as long as they come from the same thread, which will also prevent data races. We could allow any references, any kind of aliasing, as long as we guarantee that while we're accessing the object, there are no other threads that can perform updates. So this is like a const, but with a guarantee that there are no mutable aliases at the same time. And finally, we can use locking. Think of this as Java style synchronized. So whenever we call a method, we take a lock, and then when we exit, we release the lock. With the exception of the read capability, or the read mode, the modes guarantee mutual exclusion. So if we think about this for a while, if there were objects that were only reachable through one of these capabilities, via one of these capabilities, then this object should also sort of inherit the protection provided by the outer capability. And we capture this in what we call the subordinate mode. So the subordinate mode points to an object that relies on being encapsulated in some aggregate. So if the dominating capability is linear, we know that we cannot access this from outside because we would have to go through the dominating capability in order to get there. So if you're thinking about ownership types, think of this as rep or owner, sort of. We introduce capabilities by using traits. If you haven't seen traits before, you can think of them as interfaces with abstract fields. So it's saying, if I'm included in a class that provides a field count, then I'm going to provide a method called inc that increments this thing. So similar to Java 8 style interfaces with default implementations. Here's another trait that just says if there's a field count, then I'm going to return I have a method that returns the value of this thing. And then we add a mode to control why, or to specify why the capability is safe to use. So for example, linear inc is an increment capability that is globally unique. A locked inc is an increment capability that is implicitly synchronized using locks. A read inc would be a read-only increment capability, but this will not be well formed since we're performing updates in this trait. But on the other hand, a read get would be fine because we're only performing reads. So let's get, oh yes. As is common in trait-based systems, we build classes by composing traits, or rather composing capabilities. So there's a little plus symbol here. I'll get to what that means exactly in a minute, but for now just think of them as a way to compose capabilities. So the classes specify a number of traits, and for each trait it says why is this unit of functionality safe to access. So going back to our example with the counter, we could build a thread local counter by composing the increment capability with the thread mode and the get capability with the get trait with the read mode. And this way we know that these two counters cannot alias because we've said that the local counter is a thread local thing. Using the same traits, we could build a shared counter that is implicitly synchronized by locks. And so we would know that all of these accesses would be properly synchronized. So there might be high-level data races, we might not have determinism, but we are guaranteed to be free from data races. From the composition here, we see that inc and get, they might be sharing state. So we need to wrap all the methods in the get trait in locks as well. But as we have a static guarantee that the read trait is only going to perform reads, we can implement this efficiently by using a reader's writer lock. Also in the paper we talk about how you can go from having a linear plus read and then temporarily forgetting the linear part, mutable part, and then creating an unbounded number of aliases and operate on them possibly in parallel, and then get the original capability back. This is similar to what you could do with fractional permissions, for example. So, when composing capabilities, if we use the plus symbol, this is a capability disjunction. You should think about this as you can use this capability as an A or a B, but not both at the same time, not both in parallel. And this is because A and B might be sharing state. So if we think about it, capabilities that don't share any underlying state, they should be useful in parallel. For example, here are two traits that require different fields. So we should be able to compose them in a way that allows us to operate on them in parallel. And that's what we use the capability conjunction for. So this A times B means that this capability can be used as A and B and possibly in parallel. So the way we do this in practice is we can take we can create a pair like this, and then we can unpack it or split it into two aliases that we can then operate on in parallel, and then when we're done we can pack them back together, we can put them back together. So note here that in the middle step F and S are actually aliases of the same object, but they are guaranteed to access disjoint parts of the object. In the paper we also have a kind of nested composition that allows us to take a tree of pairs and create two aliases where one alias can only access the first part of each element and the other alias can only access the second part of the elements. Going back to the tree, we see from the composition here that we can split each node into two, and we can create new threads for each split. By linearity, we know that there can be no aliasing nodes, so the divide and conquer style parallelism is okay to use. From the rest of the system, we know that if there are elements that alias, then this aliasing will be thread safe. And by using subordination, we know that the elements can encapsulate the state that they need to keep private for themselves. And if you look at this, this is actual code from the paper now, and it actually looks surprisingly straightforward. I mean, there's a bunch of types here, but otherwise the bottom part looks like the kind of code that you would like to write, or I would like to write anyway. So as we've already seen, we can take the same trait and we can reuse it. We can use it in different classes that give different concurrency properties. So we can use the traits for different concurrency scenarios, and this way we can separate the business logic part from the concurrency concerns, which is captured by the modes. And what's neat about this is that the implementer of the trait can assume exclusive access to the trait. So when we're writing this code, we can focus on, okay, so I'm in this object and I have exclusive access, so what is it that I want to achieve? What is the functionality I want to provide? And then it can rely on the concurrency control to be provided later through one of these modes. These annotations, they only appear when declaring types. So we sort of move the annotations from where we use the alias to where we declare the alias. And this means that there's no effect system needed, there are no tracking of ownership types needed. Now, very briefly, we've formalized a simple object-oriented language with structured parallelism and reader-writer locks. And then we put this type system on top. And the main property we show is that well-formed programs preserve what we call safe aliasing. So basically that means that two aliases will always be composable, so they're accessing disjoint parts, or they will be synchronized using a lock, or they will both be thread local, and so on and so forth. On the implementation side, we are implementing this in the context of Encore, which is an active object language, and we're using the reference capabilities to facilitate safe sharing between active objects. So what we've tried to do in this system now in this submission is to capture the fundamental building blocks for this. But going back to this example, just applying some straightforward type inference, we should be able to simplify this a lot by just inferring these types, and possibly we could even go further and just infer the actual split, so that we use the same alias here, but we can see that all of these three parallel applications, they're using disjoint parts of the object, so we can allow this thing. Looking at a sort of a lot bigger picture, we're envisioning like a larger hierarchy of capabilities. So I've talked about some of these. I haven't talked about the unsafe. That's maybe an unfortunate name, but what we mean by unsafe is that an unsafe capability doesn't provide any concurrency control of its own. So in our system, we require you to take a lock externally. So the locked capability is implicitly locked, and the unsafe capability needs to be explicitly locked. But that also allows us to do multi-operation atomicity by taking a lock and then performing operations, or even multi-object atomicity by locking several objects and then performing operations on them. So we're not necessarily saying that we should use all of these, we should have all of these keywords. I mean, there's quite a cognitive load with this. So rather, this might be something more what you would like to use as a programmer. But by having all of these things, which are things that there are things that appear in the wild, but by having them in the system like this, it allows us to reason about their interactions. So it turns out that using reference capabilities, we can answer many of these questions. And the modes capture the programmer intent to why an object is thread safe, and through their composition we can see how we can how we can apply parallelism in a safe way to these things. And we're very much looking forward to continue exploring this style of programming. Thank you very much.
So it's very clear how all this work is targeted about reasoning about avoiding data races and inconsistencies that result from that under composition. What about reasoning about avoiding deadlock, and when do deadlock dangers happen under composition?
Right. So this is something that we haven't addressed at all in this work. So we're just as prone to deadlocks as anyone else would be. So I don't really have a good answer for how we could how this system could help avoid deadlocks, but I would think that many existing approaches should be applicable, since we're basically just reifying patterns that are already out there.
Yeah. One question about when you make a system like this, I mean, is how is it going to work in practice? It's very difficult to tell. You know, how brittle is it? I think is the question. It's a very difficult question.
Brittle in which way?
Like the type system, you know, you have this linear constraint, and it turns out that, you know, because of the actually doing the type checker, the type checker just gets too stupid at some point, and a perfectly reasonable program, it fails on just because it has to be conservative. So it's very difficult to tell. So what's your impression of that?
I agree that without an implementation, it's very hard to tell how this is going to work out in practice. But we can look at languages like Rust that uses some form of linearity in a way that seems to be working out for them. And some of the work that I haven't talked about here is actually making things like linearity more easy to handle, for example, by using different kinds of borrowing or sort of relaxing linearity for a certain scope. So that's the next step is getting an implementation out there and looking at case studies to see how it actually works out.
So I noticed you have these capability disjunction and capability conjunction operators, and it seems that they're associated with separation. So for the disjunction, you don't use those capabilities at the same time. For the conjunction, you don't use the same memory, like a separation logic style.
Right.
Do you think that list of operators, this sub-language, is complete, or do you have any vision about things you could add to make that more powerful? Because it seems that is the mechanism that allows you to use a large set of capabilities in a more nuanced way to actually get a lot of expressive power.
Right. So it's hard to know sort of these two composition operators. They allow us to capture a lot of the patterns that we've been trying to capture. So what we don't capture at all, for example, is the temporal notion. So if you look at things like behavioral types, you have capabilities where you say that first you can call this method, and then the thing changes type into something where you can call these three methods. And it's possible that something like that could be usable. There's also that's not really a composition of capabilities per se, but having a capability that somehow governs access to multiple objects could be usable somehow. You could have let's say you have a list with a first and a last pointer. You can have a single capability that guards access to either the first or the last pointer, not both at the same time. But yeah, so we can capture a lot with these things, but it's possible that there are more operators that would add functionality.
You go first.
I was just going to skip one point when you were talking about subordinate capabilities. You used an analogy of thinking about it as ownership types, and then later on, you were talking about how in this system you don't need to do tracking of things like ownership. Just wondering if you could clarify, maybe with an example, what does a subordinate thing look like? And how one
so in ownership types, you have the heap decompositioned in a nested fashion. You have these boxes, and all objects mention in their type which box they belong to. So we lose some of the fine-grained tracking of that by just saying, here's something that is encapsulated. And I don't really care if I'm pointing to my own representation or if I'm pointing to a sibling within my own box. So I can't really make that distinction. I can't make the distinction of saying, oh, here's something that is going outwards in the I can't really make the same fine-grained reasoning as I can use in ownership types. But at the same time, I also don't need to keep track of exactly where I am. I don't need to say, okay, I'm going to give this thing access to this box over here. We're satisfied with saying, I'm within a box, and that is well. Sort of. Does this answer your question?
Right. So what I wanted to ask you, basically I have two questions. So the first one is, in your hierarchy of capabilities, you've shown the unsafe. Can I think in terms of the Rust unsafe there? That's the first question. Or
if you by Rust unsafe mean that here's an escape hatch from the type system. So that's one possible interpretation of this. In the article, we didn't take that route simply because then it would be really hard to give any form of guarantees.
Yes, correct.
Really. But in a practical implementation, it could be thought about that.
Okay.
It was suggested by someone that you should think about unsafe not as unsafe, but verified by X. So you should see it as a way of sort of plugging this thing together with more expensive but fine-grained techniques. So you could say that here's something that's verified to be data-free by model checking.
Okay, so you get some guarantees then. All right, and the other thing was, but maybe we have to take that offline, but I was just wondering about the modularity of your type checking. I mean, you basically pointed out that you annotate at the declaration site, but I just was wondering whether your type checking algorithm is modular or not.
So it's completely modular. So we only have to check the traits themselves and the composition to make sure that they're well formed. And then the rest of the reasoning follows by sort of a correct by construction sort of argument, where you say, if I have something that is linear, then the only way I can move this thing is by using transfer semantics. If I have something that is locked, then all aliases I can create will also be locked, and so on.
Okay, thanks.